Okay, now let's take a look at this problem, Q3.2, from your 5th edition of your textbook. So this is a problem with the multiple flow units on multiple resources with the capacity on each flow unit is different on each resource. So I'm going to take two different approaches to solve this problem. So actually I'm gonna use this first. I'm gonna use the 1 minute of work as a flow unit. I changed my mind. I'm gonna use that first, which most of you find this more intuitive. And then I'm going to do this number of flow units per hour as the unit of analysis next. Okay, so whichever one you feel more intuitive, you're more than welcome to use whichever one you feel more intuitive. So they should lead to the identical result. Okay, so we have 5 resources with this many machines in each resource with a different processing time for each flow unit. So since we consider 1 minute of work as a flow unit, so what I'm going to do is I'm going to add your capacity, our kappa, for each resource is basically this, right? Oops, I should reference this. Okay, so because this is our capacity of each resource. Okay, and as you may recall, to answer the first question, bottleneck, you need to identify the resource or process with implied utilization rate that is higher than 100%. So now we have a kappa, and now we need to determine what is going to be the workload, which is the lambda part. Okay, so I'm going to determine the workload, which is our lambda part. Okay, so to do that, we need to know what is our demand. So we're gonna anything that talks about the demand will help. So here, this line describes our demand for product A, B, and C. Your demand per day is 40, 50, and 60. Okay, because we're analyzing this in per hour basis, so we need to break it down to per hour demand. So because it says there's 8 hours per day, we're going to divide it by 8. Okay, so this is going to be our hourly demand for each one of those flow unit. So let me BC like this. Okay, oops, let me just paste in the value, and we have it. This is our workload by number of units in each hour. But again, we're using minute of work as the unit of analysis. Then we need to know altogether how many minutes are expected. Okay, we need to get 5 unit of A, 6.25 unit of B, 7.5 unit of C. To make all these, how many minutes are expected? So to get that one, I think it is fairly straightforward. You need to rely on this information. This is an initial table provided by your textbook. So what I'm going to do is I'm going to total minutes consumed. Okay, total minute consumed. So it will be just 5 times 5 plus 5 times this plus 5 minute times, right? You can pause for a second to think about what's the meaning of this, right? So this will be total number of minutes needed or need to be consumed in order to make all those quantities when each type, each unit consumes this many minutes. So I think with that, maybe we can just drag it. Okay, maybe we can just drag it. Let's double check. Yeah, it's calculated correctly. This is also calculated correctly. Some of you may be puzzled by the meaning of 0 minute here, 0 minute per unit. That will basically means that you can make B or C in resource 3 in no minute. I think the more intuitive interpretation will be that flow unit B and C, they don't really need to go through resource 3. I think that's what it is, okay? So I think we got this right. We got all of them right. Yeah, I hope that the process so far has been somewhat straightforward. So I guess the implied utilization is basically the workload, which is expressed in the form of total minutes consumed for all those units versus total capacity that we have. So it's what it is. As you can tell that resource 3, immediately stood out as the bottleneck, because implied utilization rate is higher than 100%. It exceeded 100% by 25%. So basically this is going to be your bottleneck, right? This is going to be your bottleneck. So that's the first approach to get the implied utilization in order to identify the bottleneck. Okay. The second approach is again the number of flow units per hour approach. We basically use the count as a basis of analysis. This requires a little bit of thinking. It's not, I would say, it's not as intuitive as this approach, but it's still doable. It just requires you to think a little bit. So it's the same approach. We need to know the two critical parameter here. One is the workload lambda. The other one is the process capacity kappa. Because since we are dealing with number of units, so we're gonna have to rearrange this information a little differently this time. Okay, so I'm just gonna copy this here. Because this is a 5 minute per unit, right? Each unit requires 5 minutes. So what we need to do is we kind of have to get rid of all of them first. We kind of need to turn this into units like this. 60 minutes per hour, because we're analyzing per hour basis. 12 like this. Okay, so this, you can get rid of them because they don't really need 3, and flow unit A doesn't really need resource 4. Okay, so I guess this table is only for the case where your number of machine for each resource is 1. Okay, so here, because we need to consider this column right here, I'm just gonna get rid of it for now to make it less confusing for you. Okay, but I'm not done yet. Not done yet here. What we need to do is we need to multiply those counts by how many number of machines we have in here. Okay, so let me see what's wrong and what it doesn't like. Okay, so I guess we're fine here. Given, and now I'm gonna put this number of machines back here so that the whole table is less ambiguous. So you have the 2 machines. If you're fully dedicated resource 1 to flow unit A, you can actually make up to 24. 2 times 12 is going to be 24 here, okay? But because of the convenience of copying the whole thing, I'm just going to partially reference, I'm going to do a partial static reference on K. So when you drag it like this, it's not going to drift. What else can I do to make it like drag it downward? Let's see, what can we do? Which one do we need to fix? Which one do we need to fix? Yeah, actually, let's not try to make it overly complicated. I'm just going to repeat the same thing, okay? If you are Excel guru, you perhaps know what I was struggling earlier, but I think this will get us good enough result. So again, each machine 20 per hour. We have 2 machines, so 40. So this is good because we only have 1 machine for 1 machine here each times this guy, partially reference it, and the same thing, 2 machine K static reference like this. We go all the way here. Now we have our capacity. Now we have our capacity. Okay, capacity for each unit on each resource. Okay. However, you should be careful in terms of interpreting it, because 24 here basically means when you're dedicating resource 1 wholly, okay, entirely to flow type A, then you can make 24. But you're not only taking care of A, you also need to take care of B and C. Okay, so how does that whole thing come into play in this case? So I think that is one thing we need to handle with care. Now I'm going to move into the workload, which is the lambda part. Okay, workload. So per hour workload for A, B, and C is going to be something like this, right? It's going to be something like this. Paste the value. I'm going to take care here. So we don't have any demand here for those for this resource. We don't have any demand for A in this particular resource, because those, right? So with this, we need to calculate the implied utilization of each resource on each flow unit. Okay, so respective implied utilization on ABC. So once I finish the calculation, you can see whether the interpretation makes sense to you or not. Okay, so we have 5 units of A needs to be taken care of when this is your maximum capacity. Okay, once the resource A, for the case of resource 1, once you're done taking care of 5 units of A, you still have this much surplus capacity that you can use to take care of B and C, where B will take care this much. Well, B will consume this much capacity. So altogether, they're consuming roughly 46 or 47% or 47% of your capacity. You still have 52 some capacity that you can use to take care of C. But C will only consume this much of your capacity. So therefore, your total implied utilization here, you just use implied utilization that we are familiar with. Okay, I'm just gonna bring it down here. It's basically the sum of all respective implied utilization here. You can just do that for all of them. Okay, get rid of this, get rid of that. I think we have obtained identical result in here. Okay, so yeah, it's the relationship between this part and this part, and how they are translating into this part, that requires you to think a little bit. Okay, again, but if you feel like this part make more sense to you, you're more than welcome to stick with this approach. But this gives us a little bit more detail. It gives you more to think. Okay, so with that, let's move on to the very last question of this problem. What is the flow rate for each flow unit, assuming that the demand must be served in the mix described above? So basically, the condition is you want to maintain this ratio. Then what is going to be the flow rate on each unit? Okay, so ratio means if you want to, for each unit of A, right, I'm dividing 5 by 5 so that I can turn this into 1. You do the same process here. And for each unit of A, that means 1.25 unit of B and then 1.5 unit of C. Okay, or for each unit of B here, that basically means the fraction of A, fraction 0.8 unit of A and 1.2 unit of C. So you want to maintain that ratio. So because in our case, A becomes the a bottleneck, okay, which is 4. Other B and C, they haven't encountered the bottleneck issue, but it's only A, because A needs to go through 1, 2, 3, 5, but 3 happen to be the bottleneck, which can only give you 4. Okay, if this one were not 4, if this wasn't a 4, say if this is like a 5, right? If this was 5, and then the flow rate for A can go up to 5, and then if A is 5, and this will be your hourly flow rate. Okay, so if you look at B and C, their bottleneck is not that low. Okay, their bottleneck is not that low, so we don't have issue with the B and C. So again, straight answer is because in each hour we can only make maximum 4 unit of A. I think the flow rate per hour in this case is basically 4, right? And this is the flow rate for this whole process, just because the owner of the process wants to maintain this particular mix. Okay, so this concludes the whole thing. I hope you find this video helpful.